All right, we have 9.5, and we're starting with the integral test, and then we'll talk about the p-series test. The integral test, if f is positive, continuous, and decreasing for x greater than or equal to 1, and this is what you have to memorize for the integral test right there, and a sub n equals f of x, then the series and the integral either both converge or both diverge. If the series converges to a sum, then the remainder, the exact minus the approximation, is bounded by 0 to the integral. So they're saying that the integral is going to be the highest amount of error that we could have. So it's an upper bound. Determine whether the following series converge or diverge. And we're going to use the integral test to decide that. So we're going to say f of x is equal to x over x squared plus 1. And that is continuous, positive, and decreasing. Right, yeah, positive, continuous, and decreasing. We take the limit as a approaches infinity of the integral from 1 to a of x over x squared plus 1 dx. And we're going to let u equal x squared plus 1. So du is 2x dx. So 1/2 du is equal to x dx. Well, now we have the limit as a approaches infinity of the integral of 1/2 1 over u du. And that's the limit as a approaches infinity of 1/2 natural log of absolute value of x squared plus 1 from 1 to a. So we end up with the 1/2 natural log of infinity squared plus 1 minus 1/2 natural log of 1. Well, this is infinity, so our series diverges by integral test. Over here, we're going to let f of x equal 1 over x squared plus 1. And we're going to say f of x is positive, continuous, and decreasing. Well, now we can write the limit as a approaches infinity of the integral from 1 to a of 1 over x squared plus 1 dx. And we have the limit as a approaches infinity of inverse tangent of x from 1 to a. So we have the inverse tangent of infinity minus inverse tangent of 1. This is pi over 2 minus pi over 4. So 2/4 minus 1/4 is 1/4. So this converges to 1/4. So we say converges by the integral test. Anything down here? Nope. Approximate the sum of the convergent series by using 6 terms. Include an estimate of the maximum error for your approximation. So let's use the first 6 terms. 1 plus 1 over 2 to the 4th, 1 over 3 to the 4th, 1 over 4 to the 4th, 1 over 5 to the 4th, and 1 over 6 to the 4th. And that's equal to 1.0811235334. Well, now we're going to take the limit as a approaches infinity of the integral from 6 to a. So we're going to start where we left off with at 6. And that's going to be, let's write it as x to the negative 4th. So we're going to write this as x to the negative 4th. So when we add 1, we get negative 3 times negative 1/3. So this goes to, need the dx, limit as a approaches infinity of negative 1 over 3x to the 3rd. That's the integral, and we're going from 6 to a. Well, now we have negative 1 over 3 times infinity to the 3rd. That's going to be 0, and plus 1 over 3 times 6 to the 3rd, which ends up being the most error we can possibly have for this approximation is 0.0015432. So that's the upper bound for this approximation. a series of the form 1 over n to the p equals 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to p. That's called a p series where p is the positive constant. If p ends up being 1, then this is what's called the harmonic series because it's just 1 over n. And that diverges. The harmonic series diverges. What values of p would cause that to converge or to diverge? So let's let p equal 1. And if we do that, we have the limit as a approaches infinity, integral from 1 to a of 1 over n, or let's just call it 1 over x dx. And that goes to the limit as a approaches infinity of natural log absolute value of x from 1 to a, limit as a approaches infinity of natural log of a minus natural log of 1. Well, that's going to be natural log of infinity minus 0. So this diverges. And we said it diverges, we use the integral test. But the point is, if p is 1, this is divergent. It becomes the divergent harmonic series. What if it's 1.1? We have the limit as a approaches infinity, integral from 1 to a of, now it's going to be 1 over x to the 1.1. Let's call it x to the negative 1.1 dx. Now when we add 1, this becomes limit as a approaches infinity of, it's really x to the negative 0.1 divided by negative 0.1. So we're integrating negative 1 over 0.1 x to the 0.1 from 1 to a. But, now infinity is in the denominator, which is good. So we have plus 1 over 0.1 times 1 to the 0.1, which 1 divided by 1/10, what is that, 10? So this ends up being 10, so converges. And we said converges by, integral test. But we're really kind of showing the p-test by using the integral test. And all right, here's the other, we compare stuff to 1. So here's a value that's less than 1, integral 1 to a. Let's say it's x to the negative 0.9, because really we're looking at 1 over x to the 0.9. So we'll make it negative so that we can do the integral on this. Now when we add 1, it's x to the 0.1 over 0.1. But now the problem is the variable now is in the numerator, and that's bad for convergence. So this is 10x to the 0.1. Now when we go from 1 to infinity, that's going to be 10 times infinity to the 0.1 minus 10, but now diverges. And we're doing diverges by integral test. But it's really the p-series test that we're looking at. So on p-series test, we can say this. If p is equal to 1, this diverges by harmonic series. If p is bigger than 1, then we say converges by p-series. And if p is less than 1, that diverges. Diverges by p-series. Now here's an example that we have. Now you got to be able to look at this and know that, oh, we're going to use the p-series to this because I can get n to just this single power. This is equal to, n equals 1 to infinity, of 1 over n to the first times n to the 1/2. Well, 2 halves plus 1/2 is 3 halves. So we can write this as n equals 1 to infinity of 1 over n to the 3 halves. We can say p is equal to 3 halves, which is greater than 1, so converges by p-series. Limit comparison test. Suppose a sub n is greater than 0 and b sub n is greater than 0. And the limit as n approaches infinity of a sub n divided by b sub n is a limit. And that limit is both finite and positive. Then the two series either both converge or both diverge. So letter A, determine whether they converge or diverge. Let's compare this to n equals 1 to infinity of 1 over, how about just n squared? We could say, we can compare this to 1 over 3n squared or 1 over n squared. It doesn't matter. Well, now we say on this one, it's like we make this brand new problem. P is equal to 2, and that's greater than 1, so converges by P series. Now we go back over here and we say, well, let's take the limit as n approaches infinity of 1 over 3n squared minus 4n plus 5. And we'll divide, except we'll multiply by the reciprocal. So we'll divide by 1 over n squared, but instead of divide, we'll multiply by n squared over 1. Well, the limit of this is 1/3. This is equal to 1/3. And we say 1/3 is finite. It's not infinite, it's finite, and it's positive. And if it's finite and positive, then we can say that this series converges by what's called the limit comparison test, LCT. We're going to do something very similar over here. We're just going to look at this right here. So we're going to compare this to n equals 1 to infinity of 1 over n. Now I could say, you know, n to the 4th over n to the 5th, that reduces to 1 over n. So I could do 1 over 4n also, but that's not necessary. You can grab the 4 if you want, but you don't have to. This diverges by harmonic series. We have the limit as n approaches infinity of n to the 4th plus 10 over 4n to the 5th minus n to the 3rd plus 7. And we're going to multiply by n over 1. So really we're dividing, but since this is a fraction, we're going to multiply by the reciprocal, of course. And this limit is equal to 1/4. And we say 1/4 is finite and positive, or positive and finite. There's no order to this really. And because of that, these diverge together. So the series diverges by the limit comparison test. Letter C. Let's compare this to 2 to infinity of 1 over n to the 3rd. P is equal to 3, that's greater than 1. So this converges by P series. And let's take the limit as n approaches infinity of 1 over n to the 3rd minus 2 times n to the 3rd over 1. Now that's equal to 1. 1 is finite and positive. So they converge together. Converges by limit comparison test. Let's go with the direct comparison test. If a sub n is greater than or equal to 0 and b sub n is greater than or equal to 0, if b sub n converges and b is always bigger than a, then a must converge. Then a converges by the direct comparison test. If this one is decreasing fast enough to converge, and this one's always below it, then this one decreases fast enough to converge. And the other situation is if a sub n diverges and a sub n is always underneath, then b sub n must diverge. If this one is not decreasing fast enough to converge, and this one's decreasing slower, then this one definitely decreases too slow. So then we can say b sub n diverges by direct comparison test. Let's see how this works. Now this is a much simpler denominator. So we use this situation when we have fairly simple denominators. When we have more complicated denominators, then we're going to use the limit comparison test. So let's compare this one here to n equals 1 to infinity of 1 over n to the 3rd. Now this is a bigger denominator, so it'll be a smaller value. So we can make this claim. Now if I can show that this converges, then this one must converge. So p is equal to 3, that's greater than 1. This converges by P series. So our original converges by the direct comparison test. Over here, we're going to compare this to n equals 1 to infinity of 1 over 3 to the n. And this one here has a bigger denominator, so it has a smaller value. So 1 over 3 to the n plus 2 is less than or equal to 1 over 3 to the n. So we got to show that this one converges. If that converges, this must converge. Well, here r, this is geometric, r is equal to 1/3, absolute value of 1/3 is less than 1, so this converges by geometric series. So now we can say that our original converges by direct comparison test. This one is minusing 1 from the denominator, so let's compare it to 1 over square root of n. So this is actually the smaller denominator, which makes it the bigger value. So 0 less than or equal to 1 over square root of n, less than or equal to 1 over square root of n minus 1. Now we got to show that that diverges. If that diverges and the other one is decreasing slower, then it definitely diverges. All right, well, p is equal to 1/2, which is less than 1. So this diverges by p series. So our original diverges, well, I'll put it underneath here, diverges by the direct comparison test.